Let's say you want to transfer one shaft's rotation to the other. What's the simplest approach you can think of? Well, two rollers touching each other and operating on pure friction, right? They'd be silent too. The rollers would work great at small torque, but as you increase the load, they will begin to slip. Well, then, let's have teeth attached to these rollers to prevent slipping. Very well, but what shape? Rectangular seems like obvious. Okay, let's try it out. What do you see? There's too much noise and vibration, and the teeth are chipping off. The sharp corners of the teeth are grinding against each other. Then let's move them apart a bit so the teeth have some room to breathe. But now the efficiency has degraded. What's the purpose of a gear? What is expected from a good gearbox? Number one, should work consistently and give the same output throughout the entire rotation. Number two, good efficiency, which means less heat losses due to friction. Number three, long life, able to handle millions of load cycles. Number four, teeth do not break, surface does not pit, and the shaft does not twist. Number five, controlled backlash, which we'll discuss more in the next video. And number six, quiet, smooth, vibration free operations. Now, before going further, there isn't a universally perfect gear. Each design has its positives and negatives, and the right one is picked depending upon the application and environment, and of course, the manufacturing feasibility. One such mechanism was discovered in the 1600s by clockmakers called the cycloidal gear, but that's for another video. Today, we'll talk about gears with a specific tooth profile. The shape of the gear teeth we were stuck at? Turns out Leonard Euler solved this problem in 1765. It's called the involute. Take a spool of thread and tie the loose end to a pen and fix the spool to a piece of paper so that it cannot move or roll. Now make sure the pen is completely perpendicular to the paper and the thread is always taut. Now move the pen in the tangential direction and you'll see a curve being formed as the thread unwinds. This is the involute of the circle with the radius the same as this spool of thread. An important property of this geometry is that the thread, being a tangent to the circle, is always normal to the curve. Now take two circles and arrange them such that their involutes touch each other at a single point. Rotate the circles and it will be equivalent of a thread being unwounded from one spool and wounded to the other. You can move these circles apart or bring them together. The mechanism will remain the same. What will change is the pressure angle and the pitch circle radius. What are these? The gears are based on the original roller concept. The pitch circles are the imaginary rollers in contact with each other. They are not the same as these spools of thread but a bit larger in diameter. This thread in between the two spools form the line of action. Pressure angle is the angle between this line and the common tangent to the pitch circles. These spools of thread are called the base circles. An involute gear is a gear with the tooth flanks shaped as two involute curves in opposite directions joining together. The tips of the teeth form the addendum circle and the roots form the dedendum circle. What decides the dimensions? Turns out there are just three parameters that govern everything in an involute gear: module, tooth count, and the pressure angle. Module is basically the gap between any two given teeth of the gear. Let's say you have Z number of tooth with a pitch circle of circumference C and the gap between any two teeth as P. The circumference of the pitch circle is equal to the diameter of the pitch circle times pi, which is also equal to the gap between any two given teeth multiplied by the number of teeth we have in the whole gear. So rearranging the terms will give us that the ratio of the diameter of the pitch circle to the number of teeth we have in the gear is equal to the gap between the two teeth divided by the constant pi. And this ratio is defined as a module. For a 20-tooth gear of module 2 mm, pitch circle diameter will be 40 mm. For a 40-tooth gear, the diameter will be 80 mm. Pressure angle, defined as alpha, has been standardized to 20 degrees for all the modern gears worldwide. So if you work out the geometry, the diameter of the base circle will be equal to the diameter of the pitch circle multiplied by the cosine of the pressure angle, which comes out to be roughly 0.9397 times the pitch circle diameter. In our example, the base diameter of the 20-tooth gear with 2 mm module will be 37.59 mm, and for the 40-tooth gear will be 75.18 mm. The addendum and the dedendum are again standardized to be 1 times the module and 1.25 times the module respectively from the pitch circle. These standardizations provide enough clearance for an oil film to enter, for chips to escape during manufacturing, and for thermal expansion not to cause binding. This value was set empirically by Brown and Sharp in the 1880s and codified into ISO in the 20th century. Thus, the depth of both the 20-tooth gear and the 40-tooth gear teeth, each with module 2 mm, will be 4.5 mm. So essentially, any two gears with the same module can work together perfectly, which is very scalable for manufacturing. Now we defined P as the arc difference between any two same points on any two adjacent teeth of the pitch circle. Let's set these points as the left flanks. The gap between any two tooth of a gear will be equal to the tooth thickness and the actual gap between the two tooth. So as a design choice, it's best to have that both the tooth thickness and the gap between the two tooth, the actual gap, should be equal. So the tooth thickness comes out to be the half of P, which is nothing but pi times the module divided by 2. Hence already taken care by the module. Thus, both the tooth in our example will have a thickness of 3.14 mm. And the ideal distance between the two gears in an assembly is equal to the distance between the centers of the pitch circles, which for our example will come out to be 60 mm. As we discussed earlier, circles can move apart or come close together thanks to the involute. This allows the center distance to have tolerance for errors, which is one of the biggest reasons of the popularity of involute gears over cycloidal ones. The rest of the dimensions depend upon the application, the load, and the manufacturing process. Let's print the gears in our example with a minor change. We'll print the larger gear as 40 teeth only, but the smaller gear will be 21 teeth instead of 20. Why is it so? Tell me in the comments below. It's called the hunting tooth principle. In the next video, I'll show you how to set your model for 3D printing, and then we'll come back to the harmonic drive. See you next week.